A couple of videos ago, I spoke about the speed of gravity. In it, I said something about the force of gravity, and that unleashed a firestorm in the comment section, with lots of people admonishing me, saying that gravity isn't a force. That turns out to be an interesting question with lots of subtle, philosophical, tautological, and linguistic implications. What better way to spend the next 10 minutes or so? Is gravity a force? Betteridge's law could apply here. The law was coined by British journalist Ian Betteridge, and it states that any headline that ends in a question mark can be answered by the word no. So, if that particular aphorism is true, we have our answer. This is my shortest video ever. I'm giving Ian a break. Please share. Physics is everything. Done. On the other hand, perhaps that's a bit hasty. Maybe we need to dig into it a bit deeper. To do this right, we first need to ask ourselves, what is a force? According to Merriam-Webster, the relevant definition of force is an agency or influence that, if applied to a free body, results chiefly in an acceleration of the body and sometimes in elastic deformation and other effects. Other dictionaries say similar things. And because physics definitions are often different than colloquial ones, I dug up my freshman introductory physics textbook, Survey, if you want to look it up, and it says that a force is that which causes a body to accelerate. But it also notes that not all forces cause motion. If there are forces that counteract one another, like how gravity pulls me down but the floor pushes me up, and the net result is that I don't move. So, there are a couple of different levels of understanding gravity. The first complicated one is from Newton. He related force and acceleration. Force was mass times acceleration. And of course, force made things move. So, at least as far as Newton is concerned, gravity is most certainly a force. He didn't really know how it worked, but it was a force. One mass somehow reached across the distance and tugged at another mass, causing it to move. That, as far as Newton is concerned, is super important. What it really means is according to Newton's theoretical framework. The problem arises in 1915 when this troublemaker came up with a different theory of gravity. Combined with some insights from one of his professors, a guy by the name Hermann Minkowski, we now treat gravity very differently. In Einstein and Minkowski's formulation of Einstein's theory of general relativity, what was really going on was mass distorted space, which is a very weird concept. This picture shows you how it is often portrayed. Far from any mass, space is what is called flat, meaning you can draw it in a three-dimensional grid of straight lines. This is called Cartesian space. In Cartesian space, an object will travel in a straight line. Essentially, it follows the direction of space. This is equivalent to Newton's first law, which says that an object in motion will continue in motion unless acted upon by an outside force. However, when mass is introduced to the picture, it bends space. If you then introduce another mass, that second mass still follows the lines of space, but these lines of space are bent. Thus, in the Einstein and Minkowski formulation of gravity, gravity isn't a force like Newton claimed. Objects still move in the direction space is bent, but from the perspective of a person thinking that space is flat, they will say that the direction the object moves is curved. So the object looks like it's experiencing a force, but that's because the shape of space isn't obvious. And again, the phrase in the Einstein and Minkowski formulation of gravity is important here. It translates to the more formal, within the theoretical construct of general relativity, gravity is not a force, but rather a distortion of space. And of course, that's the origin of those somewhat stuffy admonitions. Since Einstein's theory makes better predictions than Newton's, then this settles things, right? Gravity isn't a force. Well, here is where we've gotten hasty. For one thing, we know that Einstein's theory of gravity is incomplete, and because of that, we need a replacement theory, or at least an extension, which we generically call quantum gravity. The problem is that none of the theories of quantum gravity have been validated. That means there are lots of different ways to imagine gravity at this deeper and more fundamental level. Now, I can't talk in detail about every possible alternate theory of gravity. Really, each idea should have a video of its own, and I've made a few which you can watch if you want. But here, I will instead just sketch out some ideas. Just realize that each topic will only be mentioned and not receive a deep dive. So one very simple and very common idea is that quantum gravity is transmitted by the exchange of particles called gravitons. One particle emits a graviton, which is absorbed by another, and this results in a gravitational attraction. This is very similar to the way electromagnetism works, in which one charged particle emits a photon, which is then absorbed by another, and the result is a force. Under this theoretical paradigm, gravity then becomes a force again. After all, if electromagnetism is a force, and gravity is similar to electromagnetism, then it wouldn't be unreasonable to call gravity a force too. Of course, the nature of the graviton differs in the many theories of quantum gravity. In some superstring theories, in which the smallest building blocks of matter aren't particles, but rather tiny vibrating strings, the graviton is one particular vibrational mode of a string shaped kind of like a hula hoop. At high energy, gravitons interact with particles and generate a gravitational force. In order for superstring theory to work mathematically, at the energies that are found in space, the curvature of space-time described by Einstein arises from gravitons vibrating in a coherent state, which sort of means synchronized vibrations. This looks like the curved space thing, but it has a different cause. Then there's the idea of loop quantum gravity. In this theory, space-time is quantized, which means there is a shortest distance and a briefest duration of time. In this theory, these little bits of space are attached together. I kind of imagine it like chainmail, with the individual loops held together to make a piece of armor. This paradigm is more like Einstein's model in that it is geometrically motivated, but it suffers from the fact that a path from loop quantum gravity to general relativity still eludes us. Another quantum idea is that gravity isn't fundamental, but rather it emerges from deeper principles, including string theory, black hole physics, and quantum information theory. Entropic gravity acts differently than accepted gravitational theory, and it's slower to weaken at cosmic distances. This is one possible explanation for why galaxies rotate quicker than they should. Basically, entropic gravity tries to explain the same things that dark matter does. In any event, entropic gravity invents ordinary gravity starting not from forces or geometry, but rather entropy and the statistical behavior of microscopic degrees of freedom. And there are other ideas about quantum gravity. Maybe one day I'll do a deep dive into all of them. But let's get back to that gravity is a force thing. The key thing is that understanding any physical phenomena requires a theoretical framework. In Newtonian thinking, gravity is a force. In the Einstein formulation, it isn't. And we don't know at the quantum level. If gravitons are right, then gravity is a force at high energy, but at lower energy, theories must look like the geometrical explanation. But looking like something is different than being something. After all, Newtonian gravity usually looks like Einsteinian gravity. The bottom line is that it's hasty to make any claims about the nature of gravity. It's a force, or it's a geometry, or it's caused by a buzzing of quantum particles. The answer you get depends on the theoretical framework you're using. However, stripped of theory, the true answer to the question of the nature of gravity is that it's exactly the same as when someone asks you, what's going on with you and your ex? It's complicated. Okay, that was a tricky video highlighting that our understanding of a physics thing is necessarily guided by our theories, which are both incomplete and only apply under specific conditions. Because of that, you need to be careful when you make a claim about what's going on, because you'll probably only partly right, and then only some of the time. I hope you'll like, subscribe, and share, and be sure to come back and learn more about the underpinnings of physics theories. And it's totally worth it because, well, after all, physics is everything.